All right, we'll get started a couple minutes early. So we have a test in a week, right? So we want to make sure that we get a pretty good understanding of per unit. And you've got a new homework assigned today. I try not to have too many assignments at the same time, but I did put that one out today because I know you have one due for tomorrow. But I'll give you a lot of detail on this transformer, the system example for how to do per unit. So we'll have some additional practice that hopefully will help you, excuse me, on the work. Now, one of the things that you're going to be doing is a lot of calculations, right? If you remember, we have to pick one S base. And that S base is applicable for the entire system. And then also you pick one V base in one region. So I think I said pick an S base of 100 MVA. Is that correct? So notice that S base lives everywhere where that system lives. Now I've got to define the regions. So where are the regions? Every time I go through a transformer, I go through a region. So this is region 1. Region 2. And you'll notice I have a 3-winding transformer. Call that region 3. And region 4. So maybe a better way to explain that is it's not just when I go through a transformer. How about just going through a transformer winding? So if I have a 3-winding transformer, I've got to go through to 2 separate regions. So at this point, I can pick my, yes, sir? Oh, yeah. Okay. You're right. So that we'll call that one region 5. Yes, because it does go separately. We'll see they're the same value, but yeah, that is a separate region. Yep. Okay, so we'll just pick V base over here. And I think it was, is it 13.8 kV here? Is that the lab handout? 22? 22 kV. This is the one we picked, yep. We picked a V, since this is a 3-phase system, we're picking S bases to be 3-phase or, the total MVA. And we're picking our V base to be a line-to-line voltage. Now, we just go ahead and calculate. So, VB in region 5 is the VB1, 22 kV. And then we multiply it by the turns ratio associated with T3, because T3 transfers that base voltage from region 1 to region 5. So when we check that out, we see, oops, doesn't want to scroll that way. So that goes from 22 to 110. So this right here is going to be 110 over 22. So this equals 110 kV. Yes, sir. I said transformer 3. It's hard to see. Let me erase this a little bit. May you see this transformer 3 there? Oh. That's why I use T3, not region 3. Region 2, I'm going to use transformer T1. So I look over here and I see T1 is 22 to 220. So hopefully I can do this fairly quickly. And what I see is VB in region 2 is 220 kV. Now I'm going over into region 3, which is going to be on the low sides of T2 and T4. So I'm using transformer T2 or T4, doesn't matter. So I'll just pick T2, and then I go from 220 down to 222. So BB in region 3 is 22 kV. And then lastly, I can either go from region 5 to region 4 or region 3 to region 4. It doesn't matter. It should still be the same. We'll just go region 5 to region 4, which we see we use transformer T4. Now, you'll notice with a 3-winding transformer, it's got a primary, secondary, and tertiary winding. The primary winding, we'll say it's over here. because we're going from the power side to the load side, right? This is a motor. So that's a load. We'll call that the secondary. And then this we'll call the tertiary or the third winding. Most of the time, if you have a tertiary winding, unless it's exactly the same as a secondary winding, it tends to be a lower power winding. So the primary is where most of the power comes in. That's the main winding. Secondary feeds some load, and then tertiary feeds just minor loads. So that's going from the primary to tertiary. That steps the voltage down to 4 kV. VB4 equals 4 kV. Now I've got all my regions defined, and I've got all my base voltages defined. So at this point, I'm ready to start converting impedances to a consistent base. So what I see is this parameter here. What are the units of the impedance associated with the generator? What are those units? No, it's a unitless quantity, right? It doesn't say ohms, it says 24%. So what that tells me is that is in per unit already. So this is already in per unit on a 22 kV, 80 MVA base. So all I need to do is that conversion formula. I'm not dividing and multiplying by any Z-base quantities. I'm just using my conversion formula. If you all remember, the conversion formula, is V base old over V base new, that quantity squared multiplied by SB new over SB old. And that's my equation for Z new with my Z old. So all I need to do for all these impedances that have no units, right, is use that conversion formula. These here have units, right? So those I actually have to calculate Z bases because I'm going to divide those ohm values by my Z base in those regions. Okay. So I need to make sure that I understand, or that you all understand, what the setup or the process is. Most of the parameters are given to you in per unit on the original equipment Z base. So I just need to convert those to my new system Z base, and then I use that conversion formula. The only ones that are given to me in ohms are the transmission lines. Does that make sense? Why you're not given those aren't given to you on the original equipment Z base? It's because there was no original equipment Z base. A transmission line, people are just running structures and towers. You didn't buy that from some manufacturer and say, here's the percent Z. No, that actually is designed by somebody, and you have to calculate that separately. And that's going to be calculated in ohms. So let's do the first few of them. And my suggestion is to do this in MATLAB. So we'll start a new folder. Not MATLAB, Excel. Why do it in Excel? Because these are pretty simple, easy calculations, right? I'm just multiplying and dividing whole numbers, real numbers, not whole numbers, but real numbers by values. So there really isn't any advantage to using MATLAB. You can, but why not just do simple, easy calculations in Excel and go that way? So I'm just going to pick Excel. I'll call this SB new. And that is equal to 100 MVA. So the cell in the column to the left is going to be defining what the value is. And then the actual value that I have to the right is the actual number. Now, for those of you who are whizzes at Excel, you can actually change the cell identifier from B1, and I'll just call it SB old. So whenever I write an equation, it'll automatically reference SB old. I don't have to worry about it changing or copying anything over. It just makes it really easy. All right. Now I'm going to go into my VBs. So VB in region 1, we said was 22 kV. And I'm just going to put everything in MVA and kV. And the reason why I do that is because when you do VB squared divided by S base, it's just, KV squared is mega divided by mega, so the units will cancel out. So I'll just do 100 MVA and 22 kV, and I'll differentiate that. I'll show you the units. This is in MVA. This is in kV. Now I do the same thing for VB2, and I'm just going to copy it over so I can be lazy. 3, 4, and 5. That's 2. 3, 4, and lastly is number 5. So VB1 we said is 22. VB2 is 220. VB3 was where the generator, the motor is, and that's, I believe, 22. VB4 is 110, and VB5, I think we said was 4. Let's go back and double check. 4, 110, 22. Yep, looks good. Okay. So I've got my VBs and my SBs for my new system, right? Now, if I want to go ahead and convert, yes, sir. VB, yes, for each of the regions that we've specified, wherever there's a transformer winding. Yep. That's the Z base in that region as well. Not how much impedance, that's what the base impedance is that region. So that's our ratio to set everything up. That's like our base value for how we will ratio everything. The actual impedance of a line or a transformer to that quantity. So it's like the gas tank example, right? We talked about our gas tanks are 50% full or 25% full. We don't actually care what the gas tank is. We just know that 50% full gives me 200 miles on a tank. And it doesn't matter if you're driving a pickup truck with a 40-gallon tank or, a small car with an 8-gallon tank. It still gets you around 200. And you just change vehicles. It's the same thing here. We're going through transformers and changing things, so we're getting to bigger or smaller values. That's all it is. Okay. All right, so I'll show you how to do this first one. So the very first one we have is G1 or generator 1. So if you recall, G1 is a 24% Z. So X, I'll call it G, is equal to 0.24, right? That's 24%. I don't even have to say equal to, I can just go from there. The other thing I want to do, so this is my parameter. Let's go ahead and add some terms here. We'll pick VB and SB. These are going to be the original values. So let me put one more row in here. And then I'm going to combine these by merging cells. And I'll just merge them this way. And this is going to be our original bases. So our V base originally, right, for the generator is 22 kV and 80 MVA. So this is 22, this is 80 MVA. Now we're going to go ahead and update. So we'll update here, we'll call it update. And that's going to be equal to VB old, right? So VB old, which is here, divided by VB new, we're in region 1. That quantity is squared. Then we're going to multiply that by SB new, which is here, divided by SB old. And that is my updated value. I get 1.25 times that value. Let's see if that's correct. C9 seems high though. Why is that high? Oh, I forgot to multiply it by, and then I got to multiply it by this, right? That's better. So my XG on my new base is 0.3. J.3, technically. So in my new diagram, my new per unit diagram, without any transformers, I can see that I'm going to have a generator here with an impedance, and I'm going to go to a bus. And the transformers are going to be replaced by their internal impedance. So this term right here becomes J.3 in per unit. It's not J.24, it's J.3, corrected to the new value. All right, let's do a transformer. So do you want to do T1 or T5, or do you care? T1? All right, so we'll go XT1. The original parameter is 10%. Now, the voltage, my V base, should it be 22 kV or 220 kV? Yes, sir. 220? Anybody have any votes other than 220? Who votes for 220? One brave person. Who votes for 22? A few more brave people. There's a third option. How about 220 or 220? 22 or 220? I'm voting for either one. Doesn't matter, right? On either side of the transformer, the Z base is going to work out. So you can do it on the 22 side or the 220 side. But you have to be careful. If I'm doing it on the 22 side, then my region is region 1. I'm moving everything to the low voltage side of the transformer by multiplying it by that 22 kV. So I have to divide by the V base in that region. So if I use 22, I had better use a VB1 region, base voltage. If I go to the high side, the 220 kV, then I have to use region 5. So it doesn't matter as long as you pick the right voltages. So which one do you want to use? Do you want to use the high voltage or low voltage winding? Your pick. Doesn't matter to me. All right, so we'll pick 22. The S base over here is 50 MVA. Now we're going to update it, and I'm just going to copy this over. And I know these numbers aren't right because this is the thing about Excel, right? It tries to update these cells. But notice when I picked SB original, that doesn't get updated. So there's the advantage of going ahead and calling it SBO. But the only thing that I need to change is you'll notice that it now is taking the voltage from region 2. So I have to change B3 to B2. And that becomes my updated impedance for T, is that T3? Did I say T1 or T3? T1, thank you. So on my diagram, this is J.1. Now you can do this one over here, because that's basically just the same thing that we did for T1, but doing it for a different transformer. Let's go ahead and get this line impedance. And the line impedance here is given to us in ohms. So that's in line 1 region. So I have to convert this into ohms. So I have line 1, which is 121. I have to divide that by ZB in region 2, because this has the unit of ohms. So I've got to calculate ZB2, which is VB squared, or VB2 squared, divided by SB, the new, right, or the updated one. I call that SBO, but it should be, you know, the original, or it's actually the only one that you have for SB. So that's going to be 220 kV squared divided by 100, not 1,000, 100 MVA. So now I'm ready to go here and do my line. My parameter is 121, but I don't have a VB or an SB, right? Those are the original values. I need to divide this by VB squared in that region. So this number squared divided by my S base, and I end up with J.25 ohms. So this becomes, oops, I wasn't writing, J.25 ohms. Now I have another transformer, which you should be able to do. So I'll leave that blank. I'll leave this blank. I'll leave this blank. And now I'm at the motor. Okay. So the motor is in region 3. And the motor has a 22.5%. So we'll just type that in. So this is XM. So this is 0.225. The V base in the, or for the motor, I don't know why this is taking so long, but V base for the motor is 20 kV. Uh-oh, so this has to be corrected, right? We can see that it's not matching the V base in that region, but by using that standard formula, that's okay. It automatically will correct for any voltage that is different. So we're no problem there. S base is a goofy number, 68.85. And I'm going to copy this formula over here into here. The only thing that I need to change is, actually, I don't need to change anything, right? Because it's the actual region that I'm in is region 3, isn't it? Where that motor lives is in region 3. So everything else looks like it's correct. D12 times here. D12 times B12. Where's B12? Oh yeah, that's the entrant number. So I get J.27. So my motor is going to be represented as J.27 with a power source behind it. Okay. The only thing I don't really know now is this tertiary and how to handle that. So when you have this tertiary, you kind of have to extend it a little bit because you have an impedance from primary to secondary, and you have an impedance from primary to tertiary, and you also have an impedance from secondary to tertiary, right? So this here is Z secondary to tertiary. This is Z primary to tertiary, and you can fill those out from there. Okay, so to find the secondary to tertiary, I will tell you, whenever you see this, this is the rating, the max rating that you can pull through the tertiary. So anytime you're using the tertiary value, their base quantity is always going to be based on the 15 MVA. It doesn't matter if it's the secondary or the primary, it's always the 15 MVA. Whereas primary to secondary, both of them are rated at 40 MVA. So that's what's going to be your S base value for them. The final thing we need is the load, which is delta connected capacitors. And do you remember how we talked about this class? I think it was a second or third class. We talked about the different types of loads that we have available. There are fixed impedance or fixed power loads. This one, it's better to use a fixed power load. So how do we convert that to per unit? All we need to do is call this our load. And we're going to treat it as fixed power. So I'm going to actually put this as a note. So its original value is 10 megavar, right? So that's 10. And all we need to do is divide the 10 megavar by our S base value. Whoops, why didn't that calculate? Equals this divided by this. So that's going to equal to 0.1. And it's going to be J.1 here. You will notice I did not show that as a capacitor. I showed it as an arrow. So when you're trying to differentiate between an actual load that's a power load or an actual load that's an impedance, if it's an impedance, you show it as a circuit element, resistor, inductor, capacitor. If it's an actual power load, you would use the arrow to indicate what's going on. Now, I call this J.1. Is that correct? Remember our power triangle with Eli the ice? What do you know about capacitors? What's the power factor? Is it leading or lagging? The current leads the voltage, right? In a capacitor. So here's V and here's I. So when I do my power triangle, I have P and I have Q, which means that had better be a negative J value, right? For the power, J.1. So that's the meat of the lab. You've got 1, 2, 3, 4, 5 parameters to calculate to finish off the lab. But what I'm most interested to see if you can explain it in the lab handout. Do you want to do one more? Would that help? Awful quiet. Anybody want to do one more?
Yeah.
Just 3 people? I can just do it for the back. Okay, well, for those of you who've got it, you don't have to follow. You can just start working. Which one do you want to start with? Which one do you want to do? We have the transformer T3. We have the line 2 impedance. We have the transformer T2. We have the the transformer T4. We also have the primary to the secondary to tertiary. Oops, I forgot to put this one. So we actually have 5. Right. Yeah, because this right here is primary to secondary. So so we actually have 5 of those. Sorry about that. Or 6. So we have 6 to calculate. So which one do you want to calculate? 1, 2, 3, 4, 5, or 6? Your choice. Number 6? Okay, number 6 is primary to tertiary. So I've got to go and I'm going to calculate. Over here, I'm going to go X or T4. And I'm going to add a little more detail, right? This is primary to tertiary. Because I got primary to tertiary, primary to secondary, and secondary to tertiary. So now I've got to go ahead and put in my impedance so I can see that Z primary to tertiary is 7.2%. So that is 0.072. My original VB, I'm using the most limiting winding, that's 15 MVA, or SB, I should say. And the voltage base is I can be either in this region here or in this one. It doesn't matter, right? So I can be in region 5 or region 4. It doesn't really matter. Which region do you want to move it to? Region 5 or region 4? Go ahead. Region 5. It's all right. So region 5 has the high voltage winding. So I can see here that in region 5, that's the primary. So that's 110 kV. So now I'm going to copy this over here, paste it over here, and then all I need to do is update the region. And actually, it looks like this is region 5. So I have to move it to region 4. So this one becomes B5. And if I did that correctly, that is my impedance. For that value. 0.48. And the reason why it's so much higher is because the S base, right? It went from 15 MVA up to 100 MVA. So it's going to look like a much bigger impedance. So now we just took one off the list. So let me erase this over here. And I will call this J.48. And this is Z primary to tertiary. Making sense? Do we need to do another one, or do you feel like you got it? It's not a hard process. It's just a lot of, which values do you use? But if you draw the map with the regions, I find that to be particularly helpful to go ahead and do that. Anybody need another one, or are they good? They can finish it from here. Okay, you don't have to use Excel, right? So I'm just doing it in Excel. What I can show you manually what I did. So Z primary to tertiary is equal to the original primary to tertiary impedance multiplied by the original VB divided by the new VB squared multiplied by the new SB over the old SB. So for this one, we had 0.072. We moved it to the high side, right? So the primary side. So V original is 110. V new was 110, so there's no multiplication there. And then we divided by S new, which is 100, and then S old was 15. So if you don't want to put it in Excel, you don't have to. Let me clean this up. That's how you do it. It literally is define the regions, pick your voltages, and go from there. Okay, any questions?
In the textbook, it shows that for the three winding transformer that you would kind of make a Y of the windings and convert it to that. Do you find it just simpler to keep it, I guess, with the two windings kind of in parallel with the primary and secondary?
You're talking about for a three winding transformer?
Yeah, because you've got the three winding transformer on transformer number 4.
Yeah.
And so do you just find it simpler to keep it in that format than to make it into the 3 different winding?
Yeah,
format?
I don't see how the book is doing it, because the primary and the secondary, remember what you have in a transformer, if this wakes up. Well, maybe I can't mark because it's not waking up. Sorry, hold on. So in my transformer, I have my incoming power over here, and I have 2 completely separate windings. So it's not a Y connection. It literally is 3 wires coming in and then 6 wires going out. So there is no Y. I mean, this winding could be a Y here, or it could be a delta. It really just depends on how the transformer is configured. So I'm not
Sorry, bad terminology, I guess. The way that they're doing it is creating like a fictitious center bus. And so then you've got the primary side impedance to that fictitious new bus, and then the secondary to the new bus. You've got to take the, for like the primary side to the new bus, it would be 1/2 times the quantity of the primary to secondary plus the primary to the tertiary minus the primary to secondary, secondary to tertiary. And so it's a complicated process to do that conversion. I'm
No,
sure
I
you
don't,
get the same answer.
I don't think you actually would do that. I've never seen that done in industry. They just show it connected. There's no fictitious bus. There are actually 3 independent buses there.
Well, so anyway, I just know from doing PSSE, and I've done work in Power World, they'll do it. Power World makes that fictitious bus in the 3 winding transformers in its model. It does
Well,
it like the
is that because
textbook
it's a buried,
shows.
is it a buried tertiary?
No, no, it's a regular like auto transformer, is what we're dealing with at work. And they'll take it, like I said, it'll make a fictitious bus in the middle of the transformer. And you have a primary winding side impedance to the fictitious bus, secondary impedance to the fictitious bus, and then the tertiary connection impedance to that fictitious bus. It just inserts a bus in the middle of it. PSSE does not do that.
Yeah, I'm not familiar with that. I've used Aspen, and Aspen has 3 separate buses for that as well. So I'm not, I've never used Power World, so I can't comment on that. But the way you do it in industry is it's 3, the one, like using one-liner. I've not used PSSE, but using Aspen one-liner, you would have 3 separate buses as shown.
Okay.
Because again, unless it's a buried tertiary, then perhaps you'd have that fictitious bus, right? Because the buried tertiary, there is no external winding. So then you would put a fictitious bus for that. But if it's not buried, you actually have a winding that you can access physically. And so that would be a separate bus location, an actual separate one.
All right. Thank you.
Yeah, sure. Good question, though. Oh, somebody has a chat. Let's see. Yeah, I don't know, Riley. I guess I'm not sure. Maybe they're different numbers. So unless I said to do 138 kV, did I say 138 here? It doesn't matter. I'm making it easy for you. So Riley's saying I had you do 138 here. I'm making it really easy. I'm having you pick this one over here to make it easier. Again, you have the exam in a week, so I want to make it easier for you, not harder. So I'm just making it so that for your lab, you'll pick 22 kV at generator because it makes the numbers a lot easier. Okay. Questions on that? Yes, sir.
So for your DP original, is 110.
Say that again. Do what again?
For DP original,
For which problem? Which device?
this is the
ZPT, yeah.
company said 110.
Somebody said move the voltage to the high side. So if I move the voltage, so remember this transformer right here is replaced with something that looks like this. So this is the primary winding, secondary winding, and tertiary winding. So somebody said move the per unit impedance to the 110 kV side, right? So that lives here in region 2, where I have a V base of region 2. So that's why they're both 110. I could have picked, I could have moved it to the tertiary down over here, and that would have been VB, would have been 4 kV. It just depends on which way you move it. With transformers, you can go 2 ways. You can go to the high side or you can go to the low side.
So if we did do the tertiary, would the 4 be the new or?
Well, it would be the new, but if you remember, VB on the tertiary was also 4 kV as well. So it happens to be the same for both. Right? Questions? All right, I'll give you some time to work on the lab, so I will pause the video and I'll stick around for people with questions. And we'll go from there. Yeah, so really quickly, I put J.1 here originally. That should be J.2. The J.1 was the original value. It should be the J.2, so I wrote that incorrectly. I apologize for that, but just wanted to clarify.